Right, hello everyone. Welcome to lecture 5. We're not quite halfway there, but we're nearly there. Radiation damage number 1. So this is one of 2 lectures we're going to do on radiation damage. This one we're going to introduce you to some material science. So has anyone here done any material science before? Yep, one at the back. Anyone online done any material science before? Yep, got one. Cool. 2. Nice. So apologies, this might be a refresher for you, but we're going to have to cover it so you can understand radiation damage. So here's where we're on the course. We just rearranged tritium breeding, which would have been today, but Charlotte's not around. So just swap that. It might be a nice break between the radiation damages anyway. So yeah. So today what we want to have a look at is understand the basics of a material structure and the basics of material failure, and understand sort of what radiation damage is. And then we'll have an awareness of what radiation damage does over time. But we're going to move towards that in lecture 2 and simulation methods and all that sort of malarkey in the second half. So my learning objective for you today actually is to understand this. This is a simulation. I'm not going to explain it now, but just have a think about this and what you're seeing. By the end of this lecture, hopefully you'll understand what's going on. The quality turned out okay on the big screen. So this is a video that we're going to basically go into more depth later on, but I want you to understand this by the end of this lecture. So starters, there are 2 free courses online that I fully recommend. Kai Nordland's radiation damage course, so he made the simulation you just saw in the previous slide. And Professor Mike Short's Introduction to Nuclear Engineering and Ionizing Radiation. Like half of this lecture is heavily based on his notes, partly because he does a very good job of explaining material science to normal engineers. And then a lot of the other stuff, classic Gary Waz's Fundamental of Radiation Material Science and the Shrimp textbook might be interesting. So hot off the press, if you're keeping a keen eye on the general chat for Fusion Society, this picture was posted yesterday, which is the central solenoid of ITER. It has been completed. It hasn't even been announced in the news yet, but this is a massive milestone in ITER's completion. As we've already talked about, like central solenoids, very important. And there's one of the modules. It's built of 3 or 4 of them made by General Atomics. So hopefully it will actually be installed at some point soon, which is probably when we're going to get the news announcement. All that scaffolding is just there to support it. And you can see it's actually being supported from the top as well. Yep. Thank you very much, Jack, for sending the picture in, who's currently out for Usenet. So previously, if you can cast your minds back to last week, I want you to tell me what the 2 types of laser ignition is for ICF and what film did NIF feature in. Any suggestions? We're just going to do hands rather than a survey this week, so shout it out wherever. So any ideas what the 2 types of laser ignition are? No? Iman will know. Come on, Iman. Carry the class. Oh, I can see him typing. Yep, Iman's got it. He says direct and indirect. So any ideas what the film was? This might come up in the pub quiz at the end of the course. I'm not decided yet. And it was Star Trek, a second Star Trek. Yep. So direct drive and indirect drive with your lasers, which will cause the implosion of your tritium pellets, well, tritium pellet, and that will get your fusion energy out. And the film was Star Trek Into Darkness. Nice work, Iman. So material science, what is it? So we're understanding the properties of materials and how these properties are determined by materials composition and structure. It's quite interdisciplinary, so we combine solid state physics, metallurgy, chemistry, all sorts of other bits to sort of understand the interplay between material structure, their processing methods, and their resulting properties. So we're going to focus on metals, material failure, and the effects of radiation damage. So Any ideas how materials fail? Any ideas? Just shout them out. How would a material fail? How would a part fail? How would anything fail? No answer's a stupid answer.
When they break.
Cracks? Yep. Cracking. Brittle fracture? Yep. Did someone just speak up in the chat? Fracture?
Yeah,
Yep.
when they break.
Sorry, I can't hear that, Cameron. Hold on. Let's turn my volume way up. Go on, say that again.
Basically what everyone else said, when they break.
Mm-hmm. Yep. Okay, so here's a brief list. So if we add too much stress to a material, it can break. So that's sort of overloading. If we have too much temperature, it can lower the strength, or it could just melt. You've got things like corrosion and stress corrosion cracking, fatigue, very important, cycles of loading and unloading. So you're adding stress, taking it away, or thermal fatigue, you're adding temperature and taking that away. Fracture, so you can have ductile fracture and brittle fracture, and creep is also quite important. Something we're going to focus on. So we're going to also look at the effects of radiation damage in inducing some of this failure. So we're going to look at swelling of material, void formation. Irradiation embrittlement is quite significant. So that can either form from the helium or hydrogen that exists in our environment that we've got, or the irradiation damage. Parts can activate and become radioactive and transmutate into other elements. The fracture toughness gets reduced, and you also have segregation of your alloying elements. So, has anyone seen this sort of stuff before? So you will have learned in like A-level chemistry, perhaps, that sorry, more message in the chat. Oh, sorry, Toby mentioned what is creep. Creep is a form of failure where you are at a material's about half a material's melting temperature, and it will deform under its yield stress. So that means that even though you've not got a load on it that will cause it to fail, like if it was at room temperature, if it's at elevated temperature, it will slowly deform over time, and that will lead to failure. So when we're looking at high temperature environments, that is really important. Creep is a big consideration. So in sort of A-level chemistry, you would have seen that metals have like a nice organized lattice. And whilst they go very simplified and they're all in the same plane, generally what happens is there are a few more different ways of doing it, but these are generally the ways we look at it. This is effectively how to pack spheres. So you have one way of your lattice that will repeat and is nicely organized, is your body-centered cubic. So that's a cube with you've got spheres on each corner and then one in the middle. You've got face-centered cubic, which has your spheres on each corner and then one on each face. And then hexagonal close-packed, we're not going to talk about, but that's for things like titanium and zirconium. So this is what it might look like if it's just actually spheres together. So BCC and FCC are what we're going to sort of focus on. So which one of those is this? Is this body-centered cubic or face-centered cubic? Body, it is body. So you've got your four corners and one in the middle, so it's body-centered. So we've got our nice organized structure with our repeating lattice, which is very nice and organized. But if we have defects in there, so if we've got a vacancy, which will be an atom missing from where it should be, or an interstitial, an atom in place where it shouldn't. These are what's known as point defects. They usually form in pairs, especially when we're talking about radiation, which are called Frankel pairs, because if you move one atom somewhere else, you're going to leave a vacancy behind and you've got an interstitial. Generally, it takes about 4 eV to sort of achieve this kind of thing. So it's technically possible to achieve with just thermal energy, but it'd be very close to your material's melting point. But this is generally done via radiation. So any ideas what a point defect would do to a lattice if we chucked in an extra atom in the middle? What do you think it would do? Yeah. So we're going to add an atom in like that, and it's going to stretch your lattice, which will add lots of forces, basically compressive forces pushing out, because there's an atom in place and you're other atoms in your lattice don't like that. So you basically create an extra point of force and stress inside your material. Yep, Iman, it will distort it exactly like this. So what happens if we have a vacancy? If I just remove one of these atoms, what will happen? Yeah, right, exactly the opposite. So it looks something like that. And we've got forces going the other way because the atoms are trying to fill in, but they're sort of still attached to each other with their forms of bonding. So what happens if we actually deform material? So if we add a force to this top layer, it'll break all the bonds potentially, and then we'll have some sort of shear like that, which takes a lot of energy because remember, this is 3D, so you have to break all the bonds down the plane. And then this is generally a fracture. Quite hard to do, takes a lot of energy. Iman, what's pulling into a void? For the last image, there was an atom missing, so the other atoms are essentially trying to fill in that gap. And that generally is why you've got a distortion. So what if our atoms aren't perfectly arranged? So dislocations are essentially a half plane of extra atoms that are shoved into your lattice. Right? So these are important because these are how material can deform without fracture. So we have a look at our diagram again. This is what a dislocation might look like. So you've got an extra half plane of atoms down the middle. They're out of line. They're not really organized the way they want to be. But if we apply a force to them, we don't have to break every single bond to get slip and get movement. We only have to break. So can I get the laser pointer up? Oh, yes. So we actually only have to sort of break these bonds, and then they'll sort of reattach and create new bonds over here, rather than breaking every single one at once. So that'll generally look something like that. This requires a lot less energy than the fracture we saw in the previous slides. This takes a lot less energy to do, and this leads to plastic deformation by a slip. So this is how most materials actually deform. So to have a look at this, can use something called a TEM, or a transmission electron microscope. So you use a big electron beam coming down that central column, and it passes through a very thin sample on the order of 100 microns thick. So that's very, very thin. These electrons will pass all the way through, and then we can use a detector on the other end to detect these electrons, and then we'll get some nice images out of them. Oh, so I should credit, this is actually in the basement of this building. We have two TEMs. They're both very cool, very expensive piece of kit. Also the reason you can't get signal out in the basement because they need to be isolated. And they also have a gyroscopically stable floor because you're trying to look at almost at individual atoms. You can't quite do that, but as close as you can get. So if you can jump around in those rooms and they'll still remain focused on almost an atom. So I'm going to show you some videos of dislocation movement. Don't worry if you don't understand them too much. We're just going to we're sort of breezing over a lot of material science here. But so this is one from Harry Badisha. So those black lines are your dislocations. And even though it's not very focused on this one, because it's over 10 years ago, you can see them moving around as this material is being deformed. So have a look at this one. This actually shows cross slip. You can see all your dislocations are doing something called pile up. In this case, essentially, you can almost think of them having like a charge. Essentially, they don't have one, but they essentially do in terms of the lattice tension and compression. But you can see them all piling up like a big traffic jam up there. But this is how material is generally deforming. These are moving, and your material is deforming with them. And perhaps my favorite of the three, come on. And perhaps my favorite of the three is this one, where if you have certain types of dislocations, they can actually generate more dislocations. Oh my God. Oh, hold on. My mouse has gone AWOL. Right. So we can see again, these black lines are our dislocations, our half planes that are not completely in line with our perfect lattice structure. See them moving through. And then I think this one at the bottom, as it goes in, should move now. But you can see this loop has formed And this loop is where more dislocations will catch and it'll generate sort of more dislocations, which will lead to more material deformation. Just thought it would be very cool. We don't need to specifically have a look at this. I just thought it'd be cool to see essentially atoms moving, which I think is just insane. So, come on. Oh no, I'm locked into the video. So, any ideas what happens when we've got some of our perfect crystals meeting? What happens if they're not perfectly in line? We'll get what's called a grain boundary. So, much like, I know you see ice growing, you've got lots of crystals growing together and bumping into each other. That's the same for metals. So you have essentially lots of, you can see this grain boundary down the middle. You see the atoms are sort of in a triangle shape going together, and there's like a bit in the middle where they meet. There's some missing atoms there. And this is essentially, as a defect is almost a 1D effect. If you stack lots of dislocations together, you get a 2D line, which is our grain boundary. Now, grain boundaries are important because they act as what's known as a sink. So when we had our point defects from earlier, if these defects move just through, they've got enough thermal energy to do so, they'll move to a place where it lowers the general energy in a system, and they'll just find places on grain boundaries. So grain boundaries are a place where you have lots of slip. You can also have material failure might happen. A crack might grow around a grain. But you have a lot of deformation here, and grain boundaries are very important to think about. But they're essentially a big line of dislocations, and they're just two crystals right next to each other. Are you still with me? Yeah? Cool. So another thing we need to think about is inclusions. So pretty much anything that's ever used in metals is not just a pure material. So famously steel, iron, carbon, and generally more fancy steels have a lot more additive stuff in. Like, for example, your stainless steel have lots of chromium in, so it doesn't corrode. But these different phases can form, and sometimes they'll create something known as inclusions, like particles or precipitates. So like a carbide in a steel, or chromium precipitate, and stuff like that. Or you can just have different phases. So materials will generally have a few different phases they like to sit in, and these phases will have different material properties, maybe different orientations. So like one phase might be BCC, one phase might be FCC, that sort of thing. So this graph here, well, this micrograph here, you can see the arrows to lots of carbides, some ferrite, which is essentially pure iron-ish, and perlite, which is another phase. So you've got not quite a homogeneous mix, but generally you design alloys to have phases that have good properties in certain ways. So you want this sort of thing to happen. You want your phases the way they are. You design an alloy just for that. So this is almost the end of our material science crash course. If you are generally interested, some more things to think about would be something called twinning, dislocation, slip, and glide, which you sort of almost touched on in our videos. Different kinds of dislocations, because remember, they're not actually 2D, they're 3D. If you want to have a look at a edge dislocation, look at the Royce building, it has one, because it's got a corner poking out. But yeah, we're not going to go too deep on this. We just want to have a look at our material structure and some things that matter. So what happens when a dislocation meets a defect? So this could be a point defect, this could be a big precipitate, this could be just a thing in the lattice which is unusual. So I couldn't get the video for this, but if we follow so we follow from here to here and then here to here. So you can see our dislocation line, all these atoms here, they'll move around our point defect and it'll actually bend, and it basically takes a lot more energy to deform around a point defect. So if you've got lots of defects, it's harder for dislocations and your plastic deformation to happen, and effectively your material is harder. Yeah, and I'm massively simplifying deformation mechanisms here because there is obviously a whole branch of science dedicated to it. But if you do want to learn more about material science, please ask me. So I think Toby's typing a question in chat, if I can actually get to it. Oh. Do deformations affect nuclear cross sections of the material? I don't think they do, generally the nuclear cross-section is dedicated to what atoms are in there. So if you've got lots of tungsten, which has a very low neutron cross-section, if you move the tungsten around in different shapes, it generally shouldn't impact it as much, but feel free to fact check me on that one. So this is perhaps the thing that most of you will recognize the most. Material scientists love stress strain curves because we have our little microscopic things that happen and we can try and put it into a macroscopic sense. So any ideas what toughness is? Any just a verbal description, or if you could potentially describe what it is on this graph? Area under the curve? Okay. What is toughness? Okay, yeah, I like it. What is ductility? Oh, we should know what ductility is. No? What's on this graph shows ductility? Yeah, the overall strain. What about strength? Where is what's on this graph shows the strength of the material? It's the height. It's how much it goes up. So if we have a look at it like this, so you can see the area under the graph is our toughness. Yeah, exactly how much energy it can take before it fails. Our ductility is how much strain we can put into a material. Strain is just a percentage of how much a material is extended. We've got two different points of strength. So the yield strength is where if you are below that and you stretch your material, it'll go back like a spring and it won't deform. Whereas if you go past the yield strength, it will yield and you get what's called plastic deformation, where if you then continue deforming material and then release it, it won't go back to its original length. And you've got ultimate strength there. So between yield strength and ultimate strength, you have something called work hardening. So materials will get harder as you put more dislocations into them and point defects into them, and it will essentially be harder to deform, which is why it goes up still. And then after that, you just get failure. It'll just extend without adding any more force in. And the stiffness is essentially the resilience. So if we have this graph, what would a brittle material look like on this graph? So glass fails, like it's brittle failure, so it'll smash. So what would a brittle material look like if we drew another line on this curve? Any ideas? No? Exactly that. It would, essentially almost be, and we've got it online as well, almost just the elastic, if you want to call glass elastic, almost just that. There will be no ductility in it. So whereas a copper wire, is very ductile, so this plastic deformation is a lot longer. So that'll look something like this. Oop, like that. So a brittle material will yield and then just go, whereas a ductile material will do this. So any ideas why we want let's say we have a reactor part, any ideas why we'd like it to be ductile rather than brittle? I mean, brittle materials are generally stronger, right? Yeah. I mean, the main point is they fail slower. If we have our reactor can just smash at any moment and we can't catch that and replace the part or stop the reactor, then we're in trouble. So we don't want brittle materials in our reactor. We want nice ductile materials that can absorb a lot of punishment. So some terminology. We are now done with the material science bits, essentially, and we're going to move on to radiation damage now. So just a quick bit of terminology. So radiation damage is any kind of material damage produced by radiation. Radiation, we're generally concerned with energetic neutrons and protons. So there are lots of other forms of radiation, radio waves, X-rays, whatever. We're going to be focused on, when I'm mentioning radiation, I'm focusing on neutrons and protons. Defects, as we mentioned earlier, they are atoms that are not in their regular lattice. They have been punched out by something. And deformation is when we have a material crystal or structure and it's changed. So welcome back, our 14.1 MeV neutron. This might be the most reused image in all of the lectures, but it's a good one. So we've got our DT reaction, and we did say at the start of these, if we can get the energy out of our reactor from that 14.1 MeV, we've got a power source. But the problem is that neutron will penetrate everything. Like we're on the orders of like centimeters to meters penetration into material. So what happens when a 14.1 MeV neutron hits our metal lattice? Any ideas? What happens if this hits one of those ions? Yeah? What do you think will happen as a result of that? What do you mean by? Yeah, but what physically well, it's basically bang. A neutron will hit your metal lattice and send all the atoms scattering everywhere. Toby, fission, no, this atom is actually moving too fast for fission to occur, and it's likely not going to hit anything that can undergo fission. If it was going a lot slower into a bunch of uranium, then you'd be right. Or if it was going a lot slower into a bunch of lithium to create our tritium breeding, which we're going to go on in the next lecture. So here's that simulation from the start of the lecture. So I'd like you to watch it again now that you've actually looked at some materials. So we've got basically a plane of gold atoms. This red one is a 30 keV xenon atom. So I'd like you to watch this now, and then after it's finished, I'd like you to tell me sort of what you've seen. And basically, the closer the color is to red is how much energy it's got. Okie dokie. Right, so what did we see? Feel free to say anything you think is obvious. It's not a stupid answer. Exactly. Energy dissipated, yep. So we saw a big sort of cascade and loads of damage happen. And it's mostly return to normal. The key thing is mostly. So what you can see, you can just about see they're not perfectly in line, some of those atoms. So if we have a look maybe over here, this one, over here, and over here, this backwards tick. These atoms look like they're out of plane, which means we've essentially got loads of interstitials. So neutron irradiation, so neutron or a proton. Basically, it's like making a break in a game of pool. If your pool cue is your incoming neutron, and the white ball is the first atom that it hits, the primary knock-on atom, then it hits the rest of your nice lattice, they all form a cascade. And then this will generally lead to embrittlement because you've got lots of more point defects in there, which are making it more difficult for the material to deform. So there's another simulation here, a 3D one, a very similar one. You see a cascade sort of goes out in lots of different ways, and then it returns almost to normal. And because it returns not quite to the way it was, those defects are how we build up damage. So you can see the effect of radiation on, I think this is nickel, yeah. So this is with neutrons. I think this was done in a fission reactor. So they often have test reactors where they can put material in and test it. So DPA is essentially just a measure of how irradiated something is. We can go on to DPA another time. It's almost essentially a stupid unit, but it's good enough for our purposes. So we can see the unirradiated nickel is very ductile, but then the more damage it has, the more strength it gets, but the lower ductility it has, which is quite bad because that means we've gone from a nice stretchy bit of nickel helping our reactor to something that is ready to just smash. And this could lead to easier, just even thermal shock and cracking. It could lead to any sort of failure is much easier generally with a brittle material, which we don't want. So what can an incoming neutron hit? It's essentially only two things it can hit, right? What can it hit? Yeah, it can hit the nuclei, or what else? What surrounds nuclei? Electrons, right? So basically, these are the things that it'll hit. So either hit electrons or it will hit your lattice. So electrons, in the case of neutrons, because they have no charge, almost acts as an air resistance type of effect. It's going through loads and loads and loads of them, and they are absorbing some kinetic energy. So you can see on this curve here, generally, neutrons traveling at a lower speed, higher speed, will interact more with the electron clouds surrounding ions, and this will slow it down. This will increase its interaction cross-section, and then becomes much more likely to then collide with an atom. And then it does this collision, it will then give almost all of its energy to that atom, and that will create our cascade that we saw earlier. So we'll hit one atom, that atom will hit another atom, and so on, until there's not enough energy left for a cascade to happen. This is why you get this thing called the Bragg peak. So you've got your damage going all the way through, and then it hits the point where all the neutrons will be like, right, it's time to start colliding with stuff, and they all collide and drop. We will come back to this next week because it's quite important to consider for simulating this kind of stuff. So there are generally about 3 stages for our collision to happen. So the primary knock-on atom initiates the cascade. So the primary knock-on atom is the first atom that gets hit by our neutron. This comes in here. So we're looking at 0.08 picoseconds. This initiates a cascade of collisions, and this ends when no atom has enough remaining energy to create further displacements. So it does require some energy to kick an atom off its lattice site, otherwise they'd always be falling off it. So then once they stop doing that, that's no more cascade happens. This generally creates an absolute mess, or basically a thermal spike. So the kinetic energy of the displaced atoms is shared amongst all the other atoms. The temperature rises incredibly high for a very short amount of time. Technically, the temperatures are sort of that we have here are almost instant liquidation or becoming a gas. But because it happens over such a small time scale, it's not classified as such. So the energy will be transferred away in the next stage, which is our massive quench that we saw, when all the atoms most of the atoms sort of go back to the way they were. So further collisions take the energy away, and a lot of electrons go sent very far through the lattice and get pinged off, and they transfer the energy as well. Then we have some stable defect formation, which we highlighted at the end of that video. They are the ones that remained when some atoms did not make it back to their original lattice site. And then that is your radiation damage event. So after we've done many of these, the amount of defects that survive this quench stage, the ones that were left over in the simulation, is your radiation damage. So remember, this is just from one neutron. There are lots of neutrons in a plasma, and this is happening constantly. And this whole sort of process has taken 8 picoseconds, so it's incredibly fast, which is why we don't really classify it as liquidation. So let's have a look at how damage builds up to a macro scale. So we've got our radiation processes. So one of the things that can happen is transmutation. If an atom is traveling slow enough, it can get absorbed by an atom. So a neutron is traveling slow enough, it gets absorbed by an atom, and this will undergo radioactive decay and become a different element. And then we also have our displacement damage caused by our neutron. Something else that then happens, we've got our interstitials and vacancies form. Then we also need to be concerned with hydrogen and helium because they are present. So hydrogen being in the form of our deuterium or tritium. And we've got helium, which is a byproduct of the DT reaction. This is all happening in our plasma, and these all will affect what happens next. Then we undergo our microstructural evolution. So we had a look at sort of what our microstructure might look like. So this can have like grain boundary cavities, bubbles might start forming, voids might start forming, lots of dislocations might start moving in the way we don't want them to. And then we have segregation of our alloying elements as well. So if we've got, I don't know, a phase of steel with our iron and carbon nicely together, over the course of time, they might start to separate and become a different phase, which we don't want. And this sort of leads to macroscopic effects. So you see we've got irradiation happens, it changes our microstructure, and over time that changes the macroscopic effects and things of the material. So we'll get our high temperature embrittlement, radiation hardening and embrittlement. If we think about you've got lots of voids and bubbles in your material, that will lead to swelling. Then we've got something called irradiation creep, and then also dimensional changes of your material if you've got swelling and such. So a lot of bad things happen to our material with radiation. So let's have a quick look at what different deformation looks like. So this is a nuclear steel. So we've got 6% strain and 0.8% strain there. On the left, we've got a steel that is not irradiated. And on the right, we've got a steel which has been irradiated to 4.4 dPa. So quite a lot of irradiation. And it's the same steel. So slip is something that happens when a material deforms. Atoms will like move down various slip planes, and your dislocations will move, and then your material will deform. So that's what a normal one looks like. So you've got many, many fine slip lines, all within grains. Sometimes they go into granular, but for this picture, they're all within a grain. On the right, we can see how different it is. We only have very few, much larger slip planes, which is generally why our material will deform and become more brittle in the way that it does, because it's much harder to deform an irradiated material because it's full of defects. This will then, through defect-free channel formation, which is probably beyond the scope of this, but generally it will make it harder to deform. So when it does deform, it only goes through a fewer slip lines and it goes through much more rapidly, which will then result in, okay, well, it's harder to deform, so it becomes stronger, and then it will all go at once and it'll be brittle. That is quite a simplification, but it's generally sort of what it looks like. You can see a very clear effect of radiation. If you want to know more about this, please ask me afterwards and I will wax lyrical. So voids and swelling. If you look at any nuclear-related radiation damage cause, you'll see an image that looks like the one on the right, which is our 316 steel. So this steel is generally used as a pressure vessel container for nuclear fission reactors. You can see it's grown. And why is it grown? Because, well, if we have a bunch of vacancies in the material, if they clump together, and they will, because it creates a lower stress on your lattice, if they're all together rather than lots of different places all over the place, we'll get voids. And these voids will grow, which means you've got parts of your material with no material in it, which then will lead to a size change, but also your material becomes worse because there's essentially less of it in the same volume. So you can see the size of your part has drastically changed from effectively not a lot, well, a chunk of radiation, which is something you definitely need to consider when you're designing parts. They might not fail, but they might just grow and the geometry will change and they're not fit for purpose anymore. The other thing that can happen is almost the opposite of a void, is a bubble. So if we've got lots of helium going into the surface of our material, it will happily diffuse into most metals. Helium will like to clump together and create lots of bubbles. These bubbles will grow and have almost cause a very similar effect to the growing and changing of our steel in the previous picture, but it's helium instead of nothing. Figure out which is worse? No, they're both bad. And fuzz happens on the surface of your material, which is on the right. So it's essentially almost a 2D bubble. Like if you imagine a bubble on the surface of something, it's not completed, you've got a bit of fuzz. It's essentially degrading the outside of your material. So your material's being eroded away by helium almost. It's quite bad, but it's quite a cool picture. This is my favorite image of the presentation. So as I mentioned, so if a neutron's traveling slow enough, an atom might just grab it and then start to transmutate into something else. So if we have, so this simulation is done by Mark Gilbert of the UK AEA. So if we have a part in the demo reactor, if you remember the one that's meant to come after ITER and produce power, if we have a pure tungsten part, we start with 5 different isotopes of tungsten. These are naturally occurring. So if you just made a tungsten part, this is what you'd expect to be in it. So if we actually ran this for 5 years inside of demo, have a look what other elements turn up. So we have designed a pure tungsten part because we like tungsten and its good properties. And after 5 years, it's not tungsten anymore, which is quite bad. And no, this isn't a good way to generate platinum to make lots of money. But yeah, so this is quite significant. And if your material isn't what you intended it to be, it's probably not fit for purpose anymore. So we're going to focus on the next slide. We've got tungsten, rhenium, and osmium as the main ones. So what happens with that rhenium and osmium? So because atoms are of different sizes and like to be in different places because of their charges, they will like to sort of sit in different arrangements. Because of the irradiation and the high temperature, it will often encourage movement of these different elements. So this is atom probe tomography. So this is basically like a needle that they've irradiated, and then they can sort of ablate the surface of it and then detect it. Almost like a mass spectrometer, but not quite. It's a lot more complicated, but this is how you can sort of detect what your needle is made out of. So we can actually see that even though our osmium and rhenium will have formed everywhere in our tungsten, it's actually congregated into sort of osmium core with tungsten surrounding it, the rhenium surrounding, sorry. Any idea what this will do to the material properties? Any idea? We're adding lots of inclusions that don't want to be there, which makes it harder for a material to deform, so it makes it more brittle. And tungsten's already incredibly brittle, so doing this is not doing it any favors. So sort of our overall effects. So we've got a structural material that maybe started off as an alloy, or maybe it was a pure metal like tungsten, is now transmutated into a multi-component system. It's likely got a buildup of voids and bubbles, increasing its part size and lowering its strength. Then we've got significant irradiation embrittlement and hardening due to the radiation damage and our formation of lots of interstitials and vacancies. So our materials got a lot harder. So our once ductile metal part, like you can see on this graph, so this is zircaloy 4. This is used as fuel cladding for fission reactors. You can see it was once nice and ductile. It's now incredibly brittle and almost useless. Zirconium is also interesting because rather than the 316, when it swells all in every direction, zirconium will basically only grow in one plane. It'll just get longer, for example. That's because it's HCP and not FCC, which is something I should have mentioned. So BCCs don't generally swell anywhere near as much as FCC materials do. It's not entirely known why, but there is a running theory that for a lot of things like ITER and fusion reactors, you want to use BCC materials. However, no material has been tested long enough with the sort of damage that you're going to expect in a fusion reactor to be confident it won't swell. So we haven't tested a BCC material in the same way it would be tested in a fusion reactor. So maybe BCC materials will swell. We don't know. But generally, swelling's bad. But overall, this will lead to an earlier brittle failure of material, something we just don't want. So I'd like you to have a go explaining this now that we've covered all of that. Maybe think about the different steps that occur, what was left over. I'd like just some answers of what people see, just so I know what if my rambling has stuck. BCC, as well as people can. Problem is with testing stuff for a fusion reactor is, well, we haven't got one. So that'll be included in a later lecture on design stuff and testing, because I do some sort of stuff like that. Yeah. Okay. What did we see? Come on. We've just explained it. Any idea? Anything? Just anything that you have seen over that video. Oh, sorry. We've got on the chat. Energy dissipated. Yep. Voids. Yep. We can see. Well, technically, we haven't got voids yet because that happens over time. So this is basically one neutron or one cascade happening. So over time, once many of these have happened, then we'll get voids. Dislocations, not quite. So we've got lots. So we've got, you can see a vacancy here. We've got lots of interstitials. This one is technically a cheat because it's actually not a single plane of atoms. It's a couple of planes, but it's made to look like it's 2D. How fast was the energy dissipation? So if we have a look at this step where, if we go again, yeah, very fast. It was a quench, right? So we see we've got our collision happening. We've had lots more collisions happen, and then they spread their energy all around, almost to a gaseous stage in the middle where there's like no atoms. And very quickly, that energy has been dissipated. And then once there is no energy left for any more collisions to happen, our atoms have fallen back into place, and we're left with some vacancies and interstitials, which over time will lead to our overall radiation damage and our macroscopic effects. So I think that brings us to the end. So our materials, they're based on a repeating lattice structure, be that BCC, FCC, HCP, or any of the other more complicated ones, which I wouldn't advise looking into if you want to, if you just want to stick with what you know. Defects added to this structure make it more difficult to deform materials. Radiation damage adds many defects, resulting in reduced ductility and increased strength, and generally embrittlement. Radiation damage also does a variety of other things to a metal. We've got transmutation, defect buildup, voids, growth, etc., etc. And then over time, this results in macroscopic effects, which will cause early part failure. And here's our meme of the week, because next week we're looking at tritium breeding. So thank you very much, and I'll take any questions. Anything. No question is a stupid question. If there's something like nagging on the corner of your brain, just ask it. Or you can email me or text me in the WhatsApp. But otherwise, thank you very much for listening. The main ones that you want to be aware of are, you've got BCC, body centered cubic, or FCC, face centered cubic. So BCC is a cube of atoms with one in the middle because it's in the body. And then face centered cubic is the opposite way around, where you've got atoms on all the faces because it's face centered cubic and nothing in the middle. An HCP is more of a tetragonal shape. The easiest way to think about that one is if you have a line of spheres and then you add on top another line of spheres but offset them slightly so they sit in, and then a third one on top, and that's your HCP. So are there any questions online? You're very welcome. Yeah, if you've got any questions, please ask me or text me. Yeah, I hope I haven't thrown too much information at you. Did you sort of get what I was going for with that? Do you get it? Yeah, makes sense. If you actually do want to look up more of it, I do recommend Mike Short's one. Or if you want to have a look in more of the simulation side, Kai Norden's very good. So here's where or the two videos of the cascades I've got from his website. She puts on for free, and he's really good. Yeah, I think I might end the recording there. So thank you very much for listening, and we'll see you next week for tritium breeding.